All right, so today I would like to discuss the data convergence applied to graph reconstruction, which is the third part of a series of three about graph reconstruction with on astrocyte based on calcium imaging data. So what is data convergence? So let's suppose that you have an ensemble of data sets, D1, Dn, and this can be, for example, the calcium fluctuation in region of interest acquired through a first data set 1, 2, 3, and 4. You can also imagine a permutation, which is instead of starting with 1, you start with 3, and then you move to 1, 4, and 2, and this is a classical permutation that you can make on the data. All right, so what are we calling data convergence? Well, the idea is that if you acquire a certain number of data sets, 1 to n, from which we can calculate any kind of statistical information. This can be, for example, the connectivity matrix. That is, suppose you are interested in the number of time you had a direct correlation between the node I and the node J. That is, you add 1 each time you have such an event. And so you look at the number you have in the data set n for I to j and j to I if you have a non-oriented graph, and then you just add this on this connectivity matrix. The problem is that if you have many of them and it continues increasing, you expect to have something that will not be stabilized. So it means that it basically goes to infinity as n increases. So you need to define something more refined about this notion of convergence as n increases. So we're interested in the limit for a large number of a graph and statistical quantity based on this. So you have an increasing number of data sets, and you want to calculate variables or parameters associated to the variable. So I would call x sigma of n, that is, suppose you have an ensemble of data sets from 1 to n of any permutation, and you want to compute quantity of interest, such as the matrix of connectivity, and suppose you take the limit when n is large of the quantity calculated over any permutation, and we suppose that there is a limit, and this limit is independent of the permutation. And in the end, you want to have some kind of limit, such as the graph here, where we've plotted the degree, which is for a node I, this is the number of j that are directly connected. And so the idea is that this result is independent of the permutation. And so in the data convergence, so you have your d1, dn, you have your limit x infinity. And so, for example, if you think about the connectivity matrices that could increases, in the end, as we said in the previous slide, you just look, for example, at the degree, which is the number of connection that is, for example, not 0 at large number, which is infinity, basically. And this will give you the degree of the limit graph. And you can be interested in other quantities, such as the ebb, which is a fraction of node that can be connected to a large fraction of the other node. Let's say, for example, if you fix alpha equals 80%, you want to have the node that are close to 80% of the maximum degree. And you can calculate other quantities. So, for example, for this, you can calculate the mean, the standard deviation, as your number 1 to n increases. You can also look at the length or the area of the area covered by pass, if you remember the pass in the previous YouTube. So, for example, now you can look at the connectivity matrix, and you can always renormalize it. That is, you look at, for example, a certain proportion of the maximum. And what is interesting is that if you look at your row of interest, here we took two different regions, is that after some times you see appearing region of more connected, higher dense connections, which are of interest if you are interested in the network and how they are organized. So the way it works, you can split your data set N between N1 and N2, where basically you can start with N1, you increase your data set, you choose a certain number of variables of interest, such as the mean and variance of the graph node degree, or as we said, the mean path length, the number of Hub astrocytes or neurons, whatever you're interested in, whatever the signal is coming from. And so as N increases, you are looking for the moment where you have little variation as you approach the final data sets that you have. And of course, you need to check the convergence, which is similar if you are changing the order or any permutation. It should give you basically the same value in the end. So in the case that we had at hand in the previous YouTube on this, we started with few 5U increases up to N. And so just this is in the associated publication. We see that, for example, as N increases, you can see that the mean node degree start to reach a plateau. This is normalized. It's the same for the variance. For the mean path length, it's clear that after N equals 10, you have really a nice convergence. Also, you can see a drift suggesting that possibly more data would be needed. But I would say after this N equals 13, you reach a reasonable amount of data, such as you have your variable that are slowly varying. And this is the same for the number of Hub astrocytes. After some, you can see that basically you reach a certain plateau. And the same for active area per subsection, or here the number of active ROI per subsection. Okay, so the idea is that you can study the convergence of your parameter, even if there is a small drift that can remain for other type of parameter. If some of them have reached a certain plateau, you can accept this for your data sets and your statistics. So in conclusion, in practice, you can split your data sets. An example is N equals 5 for the kind of reconstruction we had. And we could see already some convergence where N equals 10 and we went to up equal 20. You can check the convergence for permutation. This is the proof of this data convergence. And you can evaluate your graph reconstruction, looking at the connectivity matrix, the spatial statistics, and statistical property of the main parameters. It can happen that there is sometimes there can be no convergence, such as there is a drift for all parameters, or due, for example, to bleaching. It could also happen, we haven't seen that yet, that you are in a non-stationary regime of acquisition. So here, in the case of spontaneous activities, this was not the case that we had. All right, I thank you for your attention.